Bootstrap. Here I run the algorithm to make the input for scaling dimension 15, for scaling dimension 16. Here I run the input for computing the OP coefficient of the stress tensor, which is what's related inversely to CT. And so these are the various example cases. And so just to kind of show you all details, in addition to this wrapper, the only other thing you need is you need to compute derivatives of blocks. Because that is how you actually construct these polynomials, as we just explained. And so that is done by a code called scalar blocks, which is available on Docker. And so I'm running everything on Docker. And so I can just demonstrate how this works. And so, okay, so let me delete these blocks that I already made. Hopefully I won't regret that. And so then here's this code I'm running on Docker. So like, it's just one line of code. So you just run Docker. This is where the scalar blocks code is located. I'm running it in space-time dimension 3. Rmax is 40. So it's a polynomial up to 40. I want to do derivatives z and z bar up to capital lambda equals 6. I want to do it for spins between 0 and 21. This is basically saying that I'm looking at single correlators, not mixed correlators. Poles is that when you turn derivatives of blocks into a polynomial in delta, you want that polynomial to be as small as possible to make it faster. And so to make it even faster, when you write the blocks as like a sum over poles and delta, you can kind of replace those poles approximately by other poles. And that just makes the polynomial smaller. Finally, this is just how many threads on my computer to use. And then this is the precision of how many digits I want to use when computing these derivatives of these blocks.
Sorry, what did you say about replacing some poles by other? What does that mean?
So basically, when I wrote this formula before, that this G for your block of R and eta, when this thing's like written roughly speaking is sum over poles, delta minus delta m, let's say, or delta p. Right, so it has this dependence on delta. And so like say we've done this up to some cutoff Rmax. So this is going to be a finite set of poles. Say we want an even smaller set of poles, because ultimately we're going to multiply by the product of all the denominators so as to get a polynomial. So we can just replace this set of poles by another set of poles which is smaller, and that approximation you can fix the coefficients such that it's good in the regime of small, like say delta near unity.
So you're saying that that's the algorithm that's built in this?
Yeah, so yes, that algorithm is built in, and this is very useful because otherwise you'd have these huge polynomials and you'd be inefficient. And so you can kind of check in practice that this approximation works.
This just means to cut down the degree of the polynomial?
Yes, it's just to cut down the degree of the polynomial. And that's implemented in this algorithm, which is freely available. And so I just run this algorithm. As you see, it's extremely fast. Hopefully it works. And then it populates my folder with all these derivatives of z and z bar. And so if you want to look at what one of these things looks like, you can see it's just a table of polynomials in x. Because remember, x is related to delta. And so this is derivatives of blocks after multiplying by the denominator such as to get polynomials of delta, which are now converted into this variable x. And so you get one for each set of derivatives. So like this is the case of no derivatives, this is the case of derivative in terms of z, this is derivative in terms of z and z bar, etc. And then you include huge numbers of digits of precision as specified in the code, because that is what's unfortunately needed for the Bootstrap. And so this is kind of the only pre-computed quantity you really need. After you have these z and z bars, you could just run the code in the wrapper in order to compute the input for the Bootstrap. And so there's kind of an annoying technical fact, which is that, so the input which is created is something called an XML file. So here's some examples. This is what the wrapper would create. It would create this XML file for say, so this is the case where I'm assuming that the bound for spin 0 is 15. Here's where I assume the bound, is 0.15. Here's where I assume it's 0.14. Here's where instead I compute some input to compute a bound on the spin 2 stress tensor block. And so you need to further convert this XML file into a different kind of file. It's called a PVM. And so this is what, this also can be done using the Docker code. And so here, all I'm doing, okay, so let's show you an example. So say I did not have an input file. Okay, so let me kill all these input files. And so say I just had these XMLs. So if I wanted to create the input file, I would just run this PVM to STB. And so the only thing that's going on in this code, it's very simple. You just put the name of the file. The name of the file and then the precision, which is 1024. This is binary precision. So this is going to create an input file for 14, which is scaling dimension 0.14. Here I create an input file for scaling dimension 1.5. Here I create an input file for the stress tensor OP coefficient. And so this is super quick also. So as you see, it just takes a second, even just running it on my computer, just with one core. So finally, we can get to the fun part. Now that we have the input already, we can now see what happens when running the algorithm for different assumptions of this bound. And so the expectation is that we're basically trying to create the upper bound plot. So we have this plot where we fix delta phi to a certain value. So delta phi is fixed for both of these cases. It's fixed to like 0.52, which is roughly where you expect the bootstrap to be. So like this is 0.52. And then we're doing upper bounds on the bound for spin 0, and we expect basically it to be like, disallowed when it's 0.15. So this would be in the disallowed range, and then in the allowed range when it's 0.14. And so that's what we want to see for each of these two rows, as I'm going to demonstrate right now. So first, let's see what happens. Okay, so what's this code doing? All it's doing is calling the SDBB code on Docker. So this is all just copy paste. I run it with 4 cores on my laptop. Then it reads in a parameter file, which is called SDBB. It's called params.sdbb. And so params.sdbb is a set of parameters, and I will briefly give you some intuition of what they are. And so because I'm just doing the scaling dimension algorithm, that means I just want to know if the code is feasible or not. And so that's why I turn on detect feasible. And in fact, there's even something called detect primal feasible jump, which is some kind of technical thing which just allows you to see if it's a feasible point even quicker. And so I turn on all these parameters because I'm just looking for feasibility. I'm running the Bootstrap with binary precision 776, which is a pretty large value, but that's required, unfortunately. I'm using 4 processors, and then the rest of these values, okay, so this is the duality gap threshold. This is the thing I explained before. This is like, if duality gap gets smaller than this number, I say it's dual feasible. If it's smaller than this number, I say it's primal feasible. And then the rest of these things have to do with kind of initial values of your capital Y and little y. And so usually you kind of leave these things alone. I personally never change them, but maybe you could. Yeah, and so that basically, and this is the number of iterations you allow, the number of runtime you allow, and you can also create checkpoints at different intervals if you want.
Shai, what is the difference between the dual error threshold and the dual primal versus feasible threshold?
So the primal threshold versus dual threshold, because remember there's 2 different parameters. There's delta primal and there's delta dual.
Yes,
so
what's the third one?
Oh,
I'm asking about the third one, the dual error threshold.
Okay, so there's primal error threshold, there's dual error threshold. Those are the ones I've explained. And then
sorry.
duality gap threshold is this other guy. So if it's both dual and primal feasible, then you try to make it optimal, and then it's optimal when the difference between the primal objective and the dual objective is smaller than this duality gap threshold. So that's what the third parameter is. So the third parameter does not matter for the scaling dimension algorithm. You can set it to whatever you want because it's never going to be optimal. It will only matter for the OP coefficient algorithm, which we'll do next. Okay, so let's run this for 0.14. This is a point that's supposed to be allowed. And so you see it runs in real time, so this is super quick. You can just do it on your computer. And let me explain what happened. So it started with a certain guess for what the primal objective was. The dual objective is just 0. Because for the scaling dimension algorithm, we're basically extremizing a vector of zeros. Because we're not actually extremizing anything. And so if it can find a functional, then what you would expect to see is that the primal objective would go down to 0. Because it found a functional. And similarly, you would expect that these errors would go down to 0. But it can't find a functional. And so the sign that it can't find a functional is that it becomes primal feasible. Because in this context, if it's primal feasible, it will never be dual feasible. And this means you can't find a functional, which means that the point is allowed, which is what we expect. And so this algorithm goes very quickly. The algorithm which will go slightly longer is if you want to look at the point which is disallowed, so that's where you put 15. So in that case, so now what you're going to see happen is that the primal objective is going to shrink, getting closer to 0. And at the same time, you're going to find that this primal error is shrinking. And then once it gets below the threshold we put in, which is something like 10 to the minus 5, then the algorithm is going to claim that we found a dual feasible solution. So in this case, I think I put my dual feasible at actually 10 to the 10. So it's a pretty big value, but like from doing many examples, that's fine. So you kind of change that value by looking at examples and seeing like what is the cutoff which is appropriate, such that this point should really be disallowed. And so the claim here is that it found a functional, thus the point is disallowed, as we expect. Finally, I'll show you an example for the OP coefficient algorithm. So in this case, as mentioned, we expect to find an SDB which is both primal and dual feasible, and furthermore, will even be optimal. And so this algorithm is going to take longer because we're actually trying to extremize a quantity. We're trying to extremize this primal objective and this dual objective. And so what's going to happen with this algorithm is you see, like, first the primal objective is going to shrink and shrink and shrink, and the dual objective is even growing, which seems like a problem. But as long as we haven't made any mistakes, eventually, eventually the dual objective will also start shrinking. So you see, like, it goes up to some huge value. This, like 10 to the 40. The fact you're getting some huge numbers is kind of an explanation of why you need so much precision. And then eventually it starts shrinking. So now you see it's going down, and it's going to keep shrinking until the primal objective and the dual objective will become roughly equal. And then once they're roughly equal, there's going to be a bit of like oscillation, and then eventually what will happen is that this gap, which is defined as the difference between the dual gap and the primal, that's going to start shrinking itself, and then once that's below the threshold, then the program terminates. And so the threshold basically says, like, how precise do you want the bound on the OP coefficient to be? Now, you don't want to demand too much precision, because, like, this is just precision in the algorithm itself. And so, like, if we're just doing this algorithm for some fixed number of derivatives, we don't even expect to trust maybe more than 2 digits. And so that's why it would be stupid to demand that this duality gap threshold be like 10 to the minus 50. And so that's why I used a conservative value, 10 to the minus 5, which is probably even too much anyways. And so once this gets smaller than 10 to the minus 5, the program terminates, you find your optimal solution, and it spits out a number, which, as you can see here, the primal objective and the dual objective are equivalent up to 5 digits, and you get this number minus 1.0587. And so this is now the upper bound on the stress tensor OP coefficient. And so recall from these algorithms that the OP coefficient is less than or equal minus the functional acting on the identity. And so that means you do minus this quantity, so that's why it's good that it's minus. And so minus minus gives a positive quantity, and then that is the upper bound. On the OP coefficient, if you want to get an upper bound on CT, you basically take the inverse of this. And that kind of matches your intuition, because like in a reasonable normalization, you expect that CT for like the IC model should be kind of close to 1, where 1 is the CT for free theory. And so here we find there would be something like 0.95. Okay, so this demonstrates how the algorithms work, and then I can, so unless people have questions about these algorithms, I can then show you some plots which would be results of running these algorithms for many different values of delta phi and for many different values of the boundary. Okay, question?
Yeah, so you have the initial and primal. The initial values have like many orders of magnitude.
Yeah.
10 to the 30. So if you put that order 1 or something in the part where you find the solution. So 1 or 2 slides over.
I go down?
Go on the left tab. Yeah, next one over. Sorry, to the right. And once more to the right.
Okay.
Yeah, if you had put the initial P objective and D objective to be order 1, would you have...
Okay. So P objective and dual objective are computed based on what like the natural size of these derivatives of blocks are. So there's sort of kind of processing algorithm where it's like you take these polynomials in X, first you kind of normalize them by multiplying by various orthogonal polynomials, and then after that you convert it into the SDB. And so it's just a question of numerical stability. So like it turns out that they're most stable if you kind of don't change the overall magnitude of these various polynomials. And if you don't change the overall magnitude of these polynomials, after converting into matrices, it is natural that your P objective starts at this huge number.
Okay.
And so if you were to force it to some smaller number, I think it would actually hurt the numerical stability.
Can you show your input parameter file again?
The input parameter file, like these guys?
No, sorry. I mean, this file you use for the SDB parameter setting.
Here.
No.
The parameter file. Okay, good. Yeah, actually, I should make one more comment about that. So you use different parameters for, okay, so let me make one comment before you ask your question. So I showed you param.sdb, which is what you use in the case of the scaling dimension algorithm. In the case of the OP coefficient algorithm, it's difficult here. So in this case, you want to use a slightly different parameter file. In this parameter file, you don't want to end the algorithm once things become feasible. So here you turn off this find primal feasible and find dual feasible, as well as these jump parameters. And instead, and also, you then want to carefully specify this duality gap threshold, because this will basically tell you the precision of how small the thing you're extremizing is. And so this is where I said it was 10 to the minus 5. So this does matter for this algorithm, where it doesn't matter for the other algorithms. Also, sometimes you need to use more precision for the OP coefficient algorithm than for the scaling dimension algorithm, because it's somewhat less numerically stable. Anyways, but so questions about these parameter files in general. So maybe I'll open up this one as well. Okay.
I guess, okay, so you said this matrix scale, that was not something you need to adjust, but
Yeah, this is not something, okay, it's not something I have ever adjusted. I mean, perhaps one could adjust it and maybe it would improve things. But, okay, so like, let me make it clear. Okay, so what are the parameters that matter? So the parameter that matters the most in the Bootstrap is what I call capital lambda, which is basically how many derivatives of the crossing equation you take. Because the more derivatives you take, it's kind of like the bigger is your space if you're functional, and that means the more disallowed the region will be. And that's what you want, because you want to have the most stuff disallowed, so your allowed region is as small as possible. And so you basically just want to make lambda as big as possible. But you want to make it as big as possible such that your inputs still work. And what does it mean it works? It means you don't just get disallowed everywhere. And so for a given value of lambda, you then have to increase what I call Rmax and Lmax such that the Bootstrap algorithm works at all. But once you've set Rmax and Lmax to be high enough, then it doesn't change anything. And so that's why the most important thing is lambda for the number of derivatives. Second most important thing is Rmax and Lmax, because that just has to be high enough that it works. So to give you some sample value, say lambda is like 11, which is a small value to start with. That's what we're looking at right now. Then it's sufficient to have Lmax be something like 15, as well as Rmax be something like 20, which aren't like terribly big values. Okay. And then the precision parameter usually needs to be something like 500 to 700 for this simple case, which is pretty big, but unfortunately that's required. And again, like if things don't work, you'll just find disallowed everywhere. And so that's what I define as not working. It's just disallowed everywhere because it means it's too easy to find a function. Or in some perverse cases, you get allowed everywhere. But like the interesting cases, you get sometimes allowed, sometimes disallowed. Yeah, but the other parameters I don't really change so much because these are kind of parameters which kind of like involve, I guess like, how your STP, I guess it involves the initial values of the capital Y's and the little y's. And so like at least when applying STP to the Bootstrap, those don't change so much. If you're applying STP to other problems, then of course you would change these parameters.
Okay, yeah, because in my case the bounds are usually around order 1, so it doesn't make. Is there any problem with starting with a much smaller?
You'd have to play around with it. I mean, I don't have any kind of automatic rules.
Okay.
Okay, so let me just try to show some plots in the remaining couple minutes, so just so you can get an idea of what you expect to find. And these plots you can really reproduce on your computer in like 20 minutes, or maybe 30 minutes.
actually,
yeah.
one question about the algorithm. So before the divided gap goes down to 0, or when it's some small number but not 0 number, rigorously, does that mean that the one you're if you're optimizing, say maximizing, that one of the primal ideal objective that has been obtained at that stage is a rigorous bound?
You see, before you find the optimal thing?
Well, I mean, let's say even when it's indeterminate because it has that gap to be some small number, but I'm just.
Yeah, okay. So the moment it's both primal and dual feasible, then you have a rigorous bound.
Yeah, but
And then it's just how restrictive that bound is.
well, I mean, when you say it's feasible, it's up to this small.
So it's rigorous.
Right.
Yeah. So when people talk about rigor, they're always saying like rigor, numerically rigorous. It's like it's only rigorous to the extent that like you trust this these various inputs you're putting in. And, like how
you
useful.
can do better than that. I mean, just because you are not optimizing doesn't mean that.
Okay, but before you even optimize at all, you first just have to see that the STP is feasible. I mean, if the STP is not feasible, then you don't have any state. And like you decide whether or not it's feasible by whether this feasibility parameter is smaller than a certain cutoff.
No, but I'm asking about the cutoff. That's what I'm asking.
Yeah, okay. Because look, I think you only have a solution. You only have an optimal solution when the primal objective and the dual objective are identical. I think rigorously speaking. I mean, otherwise you only have a solution either to the dual problem or the primal problem separately, and you don't have a solution to both. Now, okay, maybe you could argue that because the thing you directly care about is the dual problem, that it's really only the bound on the dual objective that you care about. And so maybe you could say that even before the dual objective is the same as the primal objective, as long as you have some bound on the dual objective, that is a rigorous bound. That might be true, although don't quote me. Okay, yeah, well, let me just try to show these plots before we run out of time. So this is a plot on the scaling dimension for Z2 Bootstrap, so just single correlator, real phi's. This x-axis is what we call delta phi, which in this case I call sigma. The y-axis is delta epsilon, which is basically the bound on the spin zero operator. And so first you can look at the region, which is lightly colored, so it's this big allowed region, The point is that you just do a binary search for every single value of delta sigma. So we specifically looked at 0.52 and looked at 2 points, 1.4 and 1.5. But you can do a binary search for many values of delta sigma, and that's what gives you this upper bound. And you see that there's a kink right here, and this red point is the lattice Monte Carlo prediction for the icing model. So this was like kind of the original big result of the Bootstrap, that you got a kink where the icing model is. And so I showed 2 bounds. The first one is the gray dotted line. That was done with lower lambda, so lambda equals 11. And so that's like very quick. You can do that on your computer. Lambda 19 is just to show how it improves. And so as you see, when it improves, the point where the red dot kind of stays the same, I guess as you would expect, whereas the other things kind of slightly shrink because the logarithm gets smaller. The other kind of bound I show is when I fix this delta bound 0 to 3 and then insert an operator below. So that's what I call delta epsilon prime is 3, and now I look at delta epsilon below delta epsilon prime. And then you get both an upper and lower bound. And so that gives this kind of peninsular shape, where now this kink occurs kind of at the roughly the corner of this peninsula. And so this is kind of showing that this kink is some special point. And so far, just with a single correlator, we cannot get an island because we are only imposing that there is one relevant singlet, which is what this internal operator is, this epsilon. We have not yet imposed that there's only one relevant Z2 odd operator because that's an external operator which does not appear in the open. And so that's the best you can do just with a single correlator. So this is a plot showing bounds on the OP coefficient of the stress tensor, which is inversely related to CT. And this is a function as delta sigma. And so we're not doing any assumptions about delta epsilon. We're just leaving that at unitarity. And we're looking at bounds as a function of delta sigma. So this red line is saying where lattice Monte Carlo expects the value of delta sigma to be for the icing model. There's not really any good lattice estimates on CT, which is why it's just a line. And so what's interesting is that you find there's a minimum right where delta sigma corresponds to the icing model. And so this gray dotted line is with the lower n max. So the gray dotted line is a bit shitty. But you see that the moment you go to lambda equals 19, it already improves such that there's clearly a minimum kind of where you expect it to be. And as you go to even higher lambda, it'll become a very sharp minimum. And so this is kind of another kind of curious fact that, like, sometimes the minimum of CT also corresponds to a physical theory. So those are bounds in the case of just single correlator with no global symmetry. So now I can show you some bounds in the case of global symmetry. So in this ON bootstrap I described, which has 3 cross-union equations. So now we can look at scaling dimension bounds on different sectors. Because remember, there's 3 different representations: singlet, antisymmetric, and traceless symmetric. So let's look at the spin 0 singlet sector. And so here are bounds for different values of n. Again, the dotted line is with lower lambda, the solid line is with higher lambda, and these black dots are predictions from either large n or lattice Monte Carlo in various contexts. And again, you see that there's a kink corresponding to these predictions. And so also you see something which is, okay, and then let me show you the bound on the traceless symmetric sector. Again, you find kinks. In the traceless symmetric, okay, so one intuition you have that as n gets bigger, these bounds should get more constraining. And that is indeed something you see for these bounds on the traceless symmetric representation. So you see purple is more restrictive than red, which is more restrictive than blue. In the singlet case, it has the opposite pattern, which at first glance is a little bit confusing. The answer, though, is that when you're comparing ON to ON plus 1, the singlet of 1 is actually related to the traceless symmetric of the other. This decomposing traceless symmetric from 03 to 02 will generate a singlet. And so what you really need to compare is, say, the bound on the singlet for like 05 to the bound on the traceless symmetric of 04. And in that case, you do indeed find that as n gets bigger, the bounds get more and more restrictive, and so there's no contradiction. And so here I'm demonstrating that the bootstrap is finding these kinks corresponding to the expected theories for ON models in general, for the Wilson-Fisher fixed point, and this is something you can just reproduce yourself using Docker as discussed in today's lecture. Okay, so that's it. Any questions? We actually finished on time. So I'm happy.
Actually, can I ask you a technical question about the wrapper?
Yeah.
You have a function called icing. Can you
Yes.
just explain to me what the inputs are?
Okay, so maybe I can give a couple details about this remaining minutes before students come in and dig this out. So this wrapper, it's basically just inputting cross-chain equations into like the PMP format. So like, remember there's like 3 parts of the algorithm. You normalize something, there's a quantity you extremize, and then there's constraints. And so in all these wrappers, there's always going to be 3 quantities, which is objective, normalize, and poles. Poles are the constraints. And so for the scaling dimension algorithm, what you're extremizing is just a vector of zeros. So that's why the objective is a bit trivial. The thing you normalize in the scaling dimension algorithm, as explained, is the scaling dimension algorithm. It is the identity. Okay, so this is the icing model. So here you see objective is a bunch of zeros. The thing you normalize is just the unit operator. And then poles is just all the other operators for different spins. And so like you define poles here by basically putting in the thing that scalar blocks computed for you. And so this is basically just the thing that scalar blocks computed for you, with some slight variations. And so you have one for each spin, as you expect, up to whatever your spin count is. And so in the case of the ON model, the variation is quite small. The only novelty is that, first of all, you have three representations, singlet, symmetric, and antisymmetric. Each of them has either odd or even spins. And there's also three cross-unit equations, which is why you have a vector of these f's. And so that will apply to the poles. It also applies to the unit vector, and then it also applies to the thing you're extremizing, which is zeros. In the case of the icing CT algorithm, which is where you're extremizing an OB coefficient, so as described before, now the thing you're normalizing is the stress tensor operator itself, where we basically multiply by various factors to make sure it's normalized the way we want. Because we want literally the block, not the block multiplied by poles. That's basically what's going on here. And then the thing we extremize is the unit vector, as described in the lecture. And then poles is basically the same as the other algorithm. It's just all the various operators. And so that's all that's going on in this wrapper. So this wrapper is actually quite simple. I mean, you see it's just maybe 50 lines of code for the IC model. And the ON model is just a very slight variation. So one of the exercises is actually to write down the ON model version of the IC model. So you shouldn't cheat by looking at this. And if you just want to see how fast this thing goes, it goes quite quickly. So like here, when I run it for 0.14, this should take just like 10 seconds to run. And then this just created in my folder this XML file, which I then convert to PVM and then run as.
Yeah, my question was a bit more specific.
Yeah.
What do 0.52, 0.14, 1.6?
Oh, okay. So these parameters. So this 0.52, this is the delta phi value. So this is like where in the x-axis you're looking.
Okay.
0.52 is like where the IC model is. That's why I chose 0.52. If you wanted to make the full plot, you would want to look for many different values of this. 1.4 is the assumption for the bound in spin 0. Because this is the thing where we want to be finding either allowed or disallowed. So one case is 1.4, one case is 1.5. Sorry, before I was saying 0.14, I misspoke. I meant to say 1.4, 1.5. These other parameters don't matter. Okay, so the 1.6 you can ignore. 6 is just lambda, how many derivatives. 10, the range 0 to 15 is the number of spins. 40 is Rmax, and then 10 is like, so I mentioned you make the polynomial and delta smaller by replacing poles, so that's what this parameter 10 has to do with. So it's kind of like how many poles you keep at the end of the game. The reason why there's an extra parameter, 1.6, is that this code is general enough that you can also insert an operator. And so so that's why there's kind of an extra label, because in that case, say I want to make my bound to be 3 and then insert an operator below. So that's what so this extra parameter says what my gap is and then what the value of the thing I'm inserting is. But that's a very easy thing to change. I mean, if you guys are interested, I can even kind of show you. So in the case of this icing model, so you have the set of constraints, one for each spin, but then I also define something called inserted operator, which has the exact same form as these constraints. There's just one of them. So instead of having a table for many different spins, I just have only spin 0, and instead of having some polynomial in x is just going to be fixed to a certain value, because that's the specific scaling dimension I'm putting. Okay, so no further questions. I guess we'll wrap up for today.